Hello you beautiful people, it's time again for chemical reaction engineering, and in the last video I showed you the introduction to the Recycle Reactor, so this is part 2, and now we want to have some thoughts on the mole balance and on the concentration balance. So again, I showed you last time what is a Recycle Reactor. You have a plug flow reactor, but then you take a part of your outlet flow from the Recycle Reactor and put it back to the inlet. And this is characterized with the reflux ratio or recycle ratio. And by playing around with this R here, if you have a very high value of R, then your behavior of your new reactor, of your recycle reactor, is like a continuously stirred tank reactor. If you have a small value of R or R even 0, then you have a pure plug flow behavior. Okay, but now we want to think about the concentrations that we have here in our recycle reactor, and for this we need some things you already know from worksheet 3 and 4. So for example, this outlet concentration here, if you want to express it in terms of your conversion, then you can just rewrite Ca is the inlet concentration, Ca0 times 1 minus Xa, and then 1 plus epsilon Xa. So this we already had in the last lectures. Okay, then let's have a look. So we want to know what is the concentration at the inlet of our plug flow. So since here two streams are mixed, you have your initial inlet flow and you have your recycle flow, and this will be mixed, so you have something new, some new concentrations, and we want to find out the values for the concentration or for the conversion at the inlet. Okay, then I will do it in different colors. So here we can say, okay, our initial volume times the initial concentration plus the recycle flow times the concentration at the outlet of the reactor. This should be equal to our new unknown concentration here. Okay, so this is first the volume flow. This is our total volume flow, initial volume plus recycle times Ca in. Okay, now we can try to solve it for Ca in, the concentration at the inlet of the reactor, Ca in, is equal to V dot 0 times Ca0 plus V dot recycle times Ca over V dot 0 plus V dot recycle. Okay, what do we know about it? You can say, okay, the recycle is the same as R times our volume flow at the outlet, and our volume flow at the outlet, so V dot, hopefully you remember this, is our initial volume flow times 1 plus epsilon times Xa. Okay, and this we can use here. We can rewrite it V dot 0 times Ca0 plus, and now it's R times V dot 0 times 1 plus epsilon Xa times Ca, and you have to repeat it for the denominator. So V dot 0 plus R times V dot 0, 1 plus epsilon Xa. Epsilon. Epsilon Xa. Okay. Then we can simplify it a little bit. So in every term you have your V dot 0. So this cancels out. And the next thing that we can use is that we already know this value for CA. So we can insert CA here. Then we have CA in is CA0 plus R 1 plus epsilon XA times CA0 1 minus XA over 1 plus epsilon XA. Okay, looks quite complicated, and then we have to divide it by 1 plus R 1 plus R times 1 plus, holy moly, 1 plus, what's wrong here? One plus epsilon XA. Okay, then let's look for some simplification. So here you can see that you have 1 plus epsilon XA, and you also have it here in the denominator. So this cancels out here. And then you have CA0, so you can write it in front of your term. This means you can say, okay, this should be the same as CA0 times, and then 1 plus R 1 minus XA over 1 plus R 1 plus epsilon XA. Okay, now I have to close the brackets. Good. So basically this is one of the results that I wanted to show you with this term. So it's not looking very nice, but hope you understand what I did here. You can calculate the inlet concentration of your plug flow reactor. The next thing would be some considerations about the mole flow. And here again you can do something like a mole balance. So it should be the same. You can say, okay, let's start our inlet concentration Na0 plus the concentration that we get here from the recycle flow plus R times Na. This should be the same as N dot A in. So what do we know about this? We can say, okay, N dot A0 plus R times, and then we can say our N dot A. This should be the same as N dot A0 times 1 minus the conversion at the outlet XA. So this is N dot A0 times 1 minus XA, and this should be N dot A okay, and then we can do some rewriting. N dot A N dot A in should be the same as N dot A0, the inlet mole flow, and then big brackets 1 plus R times 1 minus XA. Okay, now we will do something weird. We will just rewrite it. So n dot NA times 1 plus R minus R times XA. Okay, and now I want to add here a term with R plus 1, or maybe 1 plus R. So if I want to add it here, then, oh, let me use different color that you 1 plus R, and then I divide it here by also by 1 plus R. So basically nothing changed. I added 1 plus R here and here, it cancels out, so everything's fine. But with this I can say, okay, now I have n dot A0, and now I can write R plus 1 minus, oops, 1 minus R over R plus 1 times XA. Okay, what did I do? I just put R plus 1 in front of my brackets, and then I have this so I removed, or I can even put some brackets here, maybe then it's more clear to see. So I removed this, so this plus 1 stands for this term, and minus R over R plus 1 times XA is the last term. Okay. N dot A in is n dot A0 times R plus 1 times 1 minus R over R plus 1 times XA. Okay, hopefully this was correct. Yes, I hope so. Okay, and what can we do with this right now? Okay, if we have a look at our inflow here, our n dot A in, we can say, okay, let's assume that this here would be our XA in. Then we can rewrite it here as n dot A in is equal to n dot A0 times R plus 1 times 1 minus XA in. Okay, what have we gained with this? Now we know that we have something like a new, this is something like a virtual inlet flow. So since we have the recycle of our volume flow through the plug flow reactor, our inlet flow is not only n.a0, but we have a mixture between the real inlet flow and the recycle flow, and we can normalize it or whatever, or express it in a new term as you can see here. So it's NA0 times R plus 1, and here we have our, this is the conversion at the inlet. So we are not starting with an unconverted flow, since we are recycling a little bit of our flow. This means we have like an initial conversion at the entrance, at the inlet of our plug flow reactor. And for this XA in, you can say this is the same as R over R plus 1 times XA. This is the outlet conversion of our real reactor. Okay. If you think, okay, maybe this was, so we just assumed something here, maybe this is not correct. I did some algebra here for you. So what you can also do to end up with an equation that looks like this. So here again, XA in is R over R plus 1 XA. This is what we had here. You can also derive it in this way. You can say, okay, this is from the first slide that we have here. You use the inlet concentration for your recycle reactor, and then you express your concentration at the inlet, just as we did it here with the conversion at any point in our reactor. And if you combine equation 1 and 2, then you will end up with some algebra, you will end up with the same equation. So hopefully this is true what I'm telling you here. I'm quite sure about it. Yes. Okay, and how can we use this right now? Okay, I showed you here with this virtual split up of the reactor. I showed if you have mole flow and you have already have an initial conversion, then your volume or your residence time, whatever, can be calculated by the inflow times this integral here. Okay, and this means now for our case, this means that we don't have n.a0, but we have to correct it with the term R plus 1. So we have to correct it here, and our XA in, this would be XA in, this can be rewritten as R plus 1 times XA, the outlet concentration. So this means if you want to calculate your volume for the recycle reactor, this is the same as n.a0 times R plus 1 integral R over R plus 1 XA to XA 1 over R dXA. Okay, and then you can play around with this here in front. You can say, okay, let's divide it by, so you can say your volume over your mole flow. This is the same as your, let me rewrite it in a different way. You can say your volume or volume flow times the concentration. This is the same as n.a0, and then you can put your, should be initial volume flow, and if you use this, if you combine these two expressions, then you can easily have your residence time is the same as volume over your initial volume flow this should be the same as your inlet concentration corrected with R plus 1. And then you have integral R over R plus 1 XA 1 over R dXA. Okay, if you compare it with what we've got already, if you say, okay, your R should be 0, then this would be pure plug flow reactor. Then for R equals 0, so what will happen if you have R equal to 0? Then you have just here the 1. So 0 plus 1 is 1. You have here, you start from the initial concentration or initial conversion of 0 to XA, and then you have the formula that we have for our plug flow reactor. Okay. Here I summarized some findings that we have now for the recycle reactor. So the outlet concentration, this you already know from the plug flow reactor, or for any case where you have changing density. Your inlet concentration can be calculated like this. Your inlet conversion is just your outlet conversion times R over R plus 1. And then your sizing of your recycle reactor, so your residence time, which is equal to the reactor volume divided by the initial volume flow, is the initial concentration times R plus 1, and then you have this integral here. Okay, what does it mean? This I will show you in the next video, how you can use this equation to get the reactor size with some graphical interpretation.